Hello. Yeah. I'm Piyush Kuru. I'm going to talk about some work which I did with Satvik Chauhan and Brent Yorgi. So this talk is about an abstraction to handle various pointer tasks in a cryptographic library that we are developing. Okay. So I'll start with monoids because they seem to capture the kind of interface we want to give for these pointer tasks. So monoids are quite familiar. They are essentially types with a binary operation which is associative and has an identity. Okay. So the familiar examples are natural numbers under addition or multiplication for that matter, and lists with concatenation. Okay. So the first problem that I want to talk about is the problem of data serialization. And for me, data serialization means writing Haskell values into buffers. Okay. And when I say I want to give a monoid interface for this, what I want to say is that semantically the identity element should look like serializing nothing, and semantically W1 times W2 should be serializing W1 followed by serializing W2. Okay. So this is semantically what it should be. Okay. So let me try to attempt at this problem. So since we are talking about writing things to buffers, the natural place to start with is functions from pointers to IO action. So a write action is something which takes a pointer to a buffer, writes some bytes to that buffer, and so since it has side effects, so it is of this type. It has a natural monoid structure. W1 times W2 is on input pointer, you apply for W1 first and then apply W2. Okay. Clearly, this is not good. We are not tracking how many bytes we are writing. And worse, W2 overwrites W1. So this is clearly not a very good serialization stuff. So the first attempt is to, let's just keep track of the length. Okay. So how do we do that? We just pair it up with integers. And on the integer side, we are thinking of the additive monoid structure. Okay. And on the write action, it is the monoid structure that we had in the previous slide. Okay. So the way we interpret a tuple W comma n is that W is the underlying action, and n is the number of bytes that the action would write if executed. Okay. So there is a natural product monoid structure, which is W1, which is given here. And notice that the lengths gets added up, so we are doing fine on the length side. But W2 still overwrites. So what do we do? Okay. So what I'm going to do is I'm going to take the same monoid structure and just tweak it a bit. Okay. So this is the tweak. So again, I will be multiplying pairs, but in a different sort of multiplication. So on the length side, I will just add up, okay, which is what we had in the last slide. But on the action side, what I do is I multiply W1 with W2 shifted by N1, okay, which is what it should be doing. So so this notation is the following: N dot W is that write action which first shifts the pointer by N and then applies W1. Okay. So if you look at this interpretation, you can see that this indeed keeps tracks of the length. Okay. It shifts W2 appropriately. Remember that N1 is the number of bytes W1 would have written if executed. So when I say W1 times N1 dot W2, what I'm doing is I am shifting W2 by as much bytes as W1 would have written. Okay. So the shifting, so W2 now does not overwrite what W1 has written. Okay. And it turns out this is a monoid. Okay. It's not so obvious from the definition, but it is a monoid, and this is essentially the semi-direct product construction. Okay. So let's look at what semi-direct product is. To define semi-direct product, we need to look at monoid actions. Okay. So what does monoid action mean? Intuitively, when you say that a monoid M acts on A, what it means is you can think of elements of M as transformations on A in a natural way. Okay. So as a type class, we can capture it by this dot operation, which takes an M and an A and gives me a new A. Okay, and these laws just says that the interpretation as transformations is natural, in the sense that the identity element of the monoid is the identity transformation, and multiplication of elements of the monoid looks like composition of the corresponding transformations. Okay. So this is what I mean by a monoid action. Okay. So M dot A would be the monoid element M acting on A. Okay. So when monoids act on other monoids, so if A itself is a monoid, then usually it is the case that I would not be interested in arbitrary actions, but something which is distributive. Okay. So the action of M should distribute over the monoid product in A. Okay. And of course, you need this annihilation property. If you are talking about groups, you could get it from here, but yeah, you need this two laws. Okay. So what it means essentially is that elements of M are not just arbitrary transformations, but they are A homomorphisms. Okay. So since we are looking at monoids, homomorphisms are the transformations to look at. Okay. So I will just keep track of this additional law through this class. This class does not have any members; it's just for these laws. Okay. So once we have the distributive action, we can build the semi-direct product, okay, which is essentially what we saw already. Okay. So this is the notation that is used in mathematics usually. So as a semi-direct product, the elements are just tuples A and N. Okay. But the multiplication is what so the multiplication is as follows. The identity element is just the pair of identity, and multiplication is on the M side you just multiply. Okay. And on the A side, what happens is that it is A1 times this M gets applied to M1 gets applied to A2. Okay. So this is the semi-direct product, and this is essentially what we saw a few slides back. So once we have this, we can build, we can get that the serialization interface we had is actually a monoid. So just a minute. So from the distributive laws, you can prove that this actually is a monoid. The distributive laws are required. Okay. So now to get back our serialization, we start with the additive structure on integers. I choose to call it the offset monoid because it kind of measures the offset in a buffer. Okay. So this just says that I'm interested only in the additive part of the, I mean the monoid structure is the additive monoid structure of it. This offsets acts on pointers by just shifting. Okay. Offset times a pointer is shift that pointer by this offset. Okay. Okay. So that's fine. We can show that this is indeed an action. So the laws are the laws for pointer action is valid. Now, so remember that we want to kind of get this action for functions. Okay. So there is a way of doing that lifting. So this is another fact that is quite well known. So if n is a monoid, then the class of functions from P to n, irrespective of what P is, that forms a monoid, which is the monoid multiplication is just pointwise multiplication. Okay. Okay. So f times g applied on P is f times P, fp times gp. Okay. So the pointwise multiplication. If you have a monoid M acting on P, then essentially you can lift it to an action on the function space. Okay. And this action is distributive irrespective of what P is. So M might not be distributive on P. In fact, P might not even be a monoid. Like in our case, P is pointers; they don't form a monoid. So it doesn't matter what it is, but this is always distributive. There is a small technical detail here which I've skipped. You need M to be commutative. Otherwise, there is this left actions and right actions, and they change. So, but for our purposes, we can assume that this works in general. Okay. So, what is this lifted action? The lifted action is the following: M applied on F is just shift by M first and then apply F. Okay. And now we come back to serialization. We start with right action. It's essentially a function from pointers to IO of unit. And the offset monoid acts on pointers, so it lifts to an action on this function space, and you just take the semi-direct product, and that's essentially your serialization. Okay. Okay. So, what is the general idea behind this construction? There is a core pointer function, in this case right action, and it is paired with offset monoid to keep track of the length. And the semi-direct product ensures that the correct lengths are calculated and appropriate displacements are done. Okay. Now let's look at deserialization. That is, you want to read some Haskell data from a buffer pointer. Okay. So the core function pointer function that I look at is this type parse action A, which takes a pointer and returns IO of A. Okay. Now let's try doing the same thing that we did for serialization. Let's pair it with the offset monoid so that it keeps track of the length in the buffer. The difficulty is that this is not a monoid because it's parametric in A, right? So how can we do a semi-direct product like construction? Okay, it turns out that the right notion to deal with this is applicative functors. Okay. So we have already seen applicative functor in the last class. There's a way of taking an element and putting it inside the functor, and there's a way of applying functions inside the functor. Okay, and the essence of this applicative loss is that it kind of generalizes the F map for multi-argument functions. Okay, I don't want to go into the details of this applicative law. What is more relevant for our setting is an alternate characterization of applicative functors in terms of these monoidal functors. Okay. So in the case of this alternate characterization is also quite well known. So you have a unit element which is of type F unit, and there is a star which helps you pair elements inside the functor. Okay. And there are certain laws it has to satisfy. The law is that unit star u is essentially u. Okay. So this just says that so why do we have an similarity instead of equal to? Because the types don't really match, but you can make it work. Okay. But if you just look at this carefully, it is essentially the laws of monoids. Okay. So the slogan here is that monoidal functors are essentially parameterized monoids. So that is the kind of slogan that I want to use in this talk. Okay. So the functor loss plus the monoidal loss gives you applicative loss. Okay. So we can do the same construction again. You can start with a monoid acting on a functor. What does that mean? It acts on f of a for each a. Okay. And these two laws just say that they are valid action on f of a. Okay, this is same as the law which we saw when monoids were acting on arbitrary types. And we need some kind of a uniformity in this action, but this is a free theorem, so we really don't have to worry about this law. This comes from this law you get for free. Okay, and when we are talking about monoidal functors, then we additionally want the condition that M should be distributive over the star. The star is the multiplication in the monoidal functor setting. And once we have this distributive law, we can form what we call the twisted functor, which is essentially semi-direct product carried out. Okay. So these definitions are the same, and I have even used the same operator here, okay, just with a change in color. Okay. So the laws, the proofs are all kind of similar because the laws are similar. It turns out that if you start with an monoidal functor f, then the resulting twisted functor is also a monoidal functor, provided the action of M is distributed. Okay. Compare it with semi-direct product is a monoid, given that you have a distributed action of M on A. Okay. So it's the same. Okay. So how does it look for parsing? Same idea. You start with parse action. Instead of taking semi-direct product, now you take the twisted functor. Okay. And then you can kind of parse, let's say, for example, 128-bit words by just parsing 64-bit and pairing it. This kind of interface would work. There is a limitation for this parsing. It can only do this kind of parsing. It doesn't have an alternate instance. So certain kinds of parsers are not easily representable here. Okay. So as a last application, I want to talk about storing secrets in memories. So what we want is we want to store sensitive information in memory, and we don't want it to be swapped out. Okay. So there are system calls to lock memory, mlock and munlock, but unfortunately they block only at the page level. So you can't use, for example, foreign pointers to just put a appropriate finalization routine, because if two buffers overlap in a page, then unlocking one would unlock the other. Okay. So you might want to, if you want to implement a secure memory, you would be forced to implement a mini GC inside your library, and this is not very good. So our solution is go for a one go allocation. Okay. So how do we do this? We have an abstract class which denotes memory elements. So essentially a memory element is a pointer, but it is wrapped inside a type so that things are controlled. And you have an allocation strategy for it, which in particular tells you how much memory you need to allocate a memory element. Okay. So it is not difficult to see that you can write such a function which takes a memory action and creates such a memory and passes it to the action. Okay. So the interesting part is this allocation strategy. How do you do this allocation? Okay. And so what it corresponds to is creating a memory element from a chunk of memory, and allocations of compound memory elements should be kind of easy to handle. What do I mean by that? Well, we define allocation action as a function from pointers to mem. Okay. And it turns out that if you take this twisted functor, where the offset keeps track of how much you have already allocated from the chunk, then you can build complicated memory allocations pretty easily. For example, consider a memory action that requires two memory functions, and we can think of it as a memory action that takes a pair of memory elements, and you can define a memory instance for this pair by just using the applicative instance, and there is no place where we actually do any explicit pointer arithmetic or something, or size calculation. Okay. Okay. So what does all this buy us? As a result of this interface, there is only one place where you define the pointer action or the offset monoids action. That is the only place where there is any explicit pointer arithmetic. Okay. All size calculations and offset calculation is done by the semi-direct product or the twisted functors, and you can generalize it further. For example, if you want all the memory elements to be allocated at memory boundaries, the alignment boundaries, this can be done. Okay. There is more in the paper, but since my time is up, I'll just stop here.
So this distributive monoidal action that you defined is, even in the deserializer case, it's an action over, like it's a monoidal action over an applicative functor.
Yeah.
Is there anything to be gained if you allow for the action itself to also be an applicative functor? Because that, like you just take normal product and also do some action instead of forcing the right-hand side to be the const functor.
I looked at it, but couldn't progress much. Maybe there are some interesting applications. So the point is that I think you have so you have a type parameter on both sides, right? You will have FA to act on FB or GB because it goes cross, right? If you go back. So if I understand your question correctly, okay, here. So this is f of a, okay, this is f of b. So this part would be some f of a, which should be acting on f of b. So I'm not sure how one can handle this, or probably one can define something, but I'm not very sure how useful it would be.
So serialization, you say, is a monoid, but maybe I want to give this right action just an argument where I can vary what I actually write to that.
Yeah, so pointer. In particular, the twisted functor generalizes that. So for example, if you just take twisted functor with type parameter being the unit, then you get essentially semi-direct product. So what you're saying is that keep track of what you're writing in the type itself, right?
Yes, and then you have a contravariant functor because it's an argument to the function.
Yeah, but can't you just use the twisted functor? So if you look at the, I've been a bit loose here. If you look at parse action, there's nothing here that says that this only reads. So you could have a write action also here.
But then what would you write there? Like what data? Where can you ever specify which data you write?
I mean, you mean this type can just be the return value? I mean, if you write something that it writes it into bytes and returns the value. So that's kept track of in the type.
I think I'll take this offline.
Okay.
Yes. Okay, please.
Hello, I'm Matthias. I just wonder if you, like the trick we have said in mathematics quite a lot, where you take a structure and then you look at its action on a set, and that you preserve the structure. Like, have people looked at that, like in the context of like programming for like rings and semi-rings and stuff like that? The action of those, because he did it for monoids and it was a nice thing. I wonder if people have looked into other actions.
I'm not sure.
Okay.
I'm not very familiar.
Okay, thanks.
Mm-hmm. Okay. So any more questions? Okay, yes.
I am aware of, I don't know too much about the technical details, but I'm aware of an algebraic structure similar to this kind of monoid with an action on it, but for groups, called a torsor over G.
Okay.
So that might be an interesting place to kind of mine for more math. It's used in algebraic geometry.
Okay. Thanks.
Okay. Yes. Any others? Okay. If no, okay. Thank you very much. Okay, for lunch.